perfect practice exercise dated for 318 or 319, depending on if you're even or odd. Answers to this need to be worked out onto page 45 in your interactive notebook. Remember that in a perfect practice video, go through and solve the problem on your own by pausing the video, then answering it on your own, and then pressing play to look through the work that is presented. Double check to see if you did the problem correctly. Make any corrections, and if you have any questions, make sure to jot them down off to the side so that you can ask them when you come back in class. There are 7 problems today for the perfect practice, so let's go ahead and get started. Question number 1. Calculate the number of moles of sodium hydroxide present in 35 grams of sodium hydroxide. The molar mass is 39.998 grams per mole. For those of you who this is your first perfect practice, go ahead and pause now. I am not going to pause. I am just going to go through and answer these straight through. So you need to pause and answer. All right, here we go. So starting off, this is a grams to mole calculation. So we're going to use our molar mass as part of a dimensional analysis. Because of the units, grams of sodium hydroxide, I want to have grams of sodium hydroxide down here at the bottom so that they cancel. So looking at the molar mass, 39.998 grams of sodium hydroxide go on the bottom. 1 mole of sodium hydroxide goes on top. This way the grams will cancel and I'm left with 35 divided by 39.998. So going to my calculator, 35 divided by 39.998 equals, and I need to round that to 3 significant figures, so it's going to be 0.875. All right, question number 2. Question number 2 says, calculate the molarity of a solution made with 35 grams of sodium hydroxide dissolved in a total volume of 0.545 liters. So looking at how we solve this problem, first off, we can list out our given. Okay, so we know that we have 35.0 grams of sodium hydroxide. We have a volume of 0.545 liters, and our unknown is molarity. The equation for molarity is equal to the number of moles divided by the volume. In this case, we need moles, and it just so happens that in the previous problem up here, we found what 35 grams of sodium hydroxide are in moles. So we're going to plug in our answer from above, 0.875 moles of sodium hydroxide. On top, the volume, 0.545 liters. The molarity is going to be equal to, pull up our calculator. So we have 0.875 divided by 0.545. Each of these numbers have 3 significant figures. So I have 3 in my answer, so it's going to be 1.61 as my answer. 1.61. 1.61. And then for our units, we have moles per liter. And the way we write that for ACE is MOL, and then liters to the -1. And then our identity of the substance that we're looking at is sodium hydroxide. So the molarity of the solution is 1.61 moles per liter of sodium hydroxide. All right, question number 3. It says, if there are 3.9 moles of sodium chloride dissolved in 4 liters of solution, what is the molarity of the solution? So once again, given Number of moles is 3.90 moles of NaCl. The volume is 4.00 liters. Our unknown, once again, is molarity, capital M. Molarity is equal to number of moles over volume. The number of moles, 3.90 moles of NaCl. Volume, 4 liters. Once again, going to our calculator, 3.9 divided by 4, we get 0.975. 3 sig figs in my answer, so I'm good to go. 0.975. And once again, the units, moles per liter NaCl. Okay, moles per liter. All right, question number 4 says write the equilibrium expression for the following reaction. Kc is our equilibrium constant based off of concentration. And the way we write this is we have our products here are on top, and then our reactants are going to go onto the bottom. So I have concentration of NaF. We use brackets to note the concentration, and because there is the number 1 in front, I want to raise this to the 1 power, which we don't need to mark. And then the second substance is H2O, so the concentration of H2O. Again, the number out in front is 1, so I do not need to raise this to any value. Then on the bottom, I'm going to start with our first reactant, which is HF. Again, no number out in front, so I don't have to raise the value to any number. And then NaOH, concentration, and again, the number 1 out in front, I do not need to raise it to any particular exponent. I do not need to put in the number 1 because anything raised to the first power is itself. Okay, these are always done the same way. Reactants on the top, products on the bottom, and we're dealing with concentrations because it's the concentrations that will become static at equilibrium, and we raise it to the coefficients that are in front. All right, question number 5 says write the equilibrium expression for the following reaction. Again, Kc is our equilibrium constant. We start by our products on top. There's only one product this time around, sulfur trioxide, but sulfur trioxide has the number 2 out in front, so I need to raise that to the second power. Then on the bottom, I have reactants. So I have sulfur dioxide. The sulfur dioxide has the number 2 out in front, so I need to square the concentration of sulfur dioxide. And then my second substance is O2. So it's the concentration of O2, and it's just raised to the 1 power, the first power. So no need to put a number in there. Writing these expressions should be very quick. It should be very, very straightforward. There's no special math that we have to do to actually create the expression. All right, question number 6. We're going to have to use our equation from question number 5. It says using that equation, calculate the Kc of the equilibrium constant for the substances are at the following concentrations. A little wording there, wrong a little bit. Let's see if we can clear that up. It says calculate the Kc if the equilibrium constant for the substances if the substances are at the following concentrations. Okay, so the concentrations listed are the concentrations at equilibrium. And remember from question number 5 up here, we know that we're going to have the concentration of SO3. We're going to square it. We're going to divide it by concentration of SO2 squared, and then the concentration of O2. Okay, so plugging in our numbers. Okay, the first value here, SO3 is the bottom number. So I have 0.590 moles per decimeter cubed squared divided by SO2 is that top number there. So, oops, 1.22 moles per decimeter cubed squared times the concentration of the oxygen, which is 0.945. Yep, forgot my units. Moles per decimeter cubed. Now, I will tell you that for tests and quizzes, we are not going to focus in on being able to calculate the units correctly. I am going to show it to you here for completion. For those of you who are going to go on to one of the ACE classes, this will be an expectation in those ACE classes that you can calculate the value of units from complex equations such as this one. So going to my calculator, I have 0.590 and I want to square it. Okay, then I'm going to do the division in stages. So I'm going to take that number, I'm going to divide by 1.22, and the 1.22 is also squared. Okay, I'm going to go ahead and hit enter now, and then hit the second division for the second number, which is 0.945. This one is not raised to any power, so my final answer is 0.247, three significant figures, 0.247. And then for my units, okay, looking here, I have moles per decimeter cubed squared, moles per decimeter cubed squared. So those are going to cancel. So unit-wise, I'm left with 1 over mole per decimeter cubed. Now, if you remember from your algebra class, if I wanted to undo this fraction, so it's all on one line, I can pull these units or these variables to the top, but I have to change the sign of their raised exponents. So moles become raised to the -1 power, and then decimeters cubed are just cubed. They're no longer a negative exponent. Okay, so the way I would write that is per mole decimeter cubed. Oops, I did it. Should be a positive number. There we go. So per mole decimeter cubed for the units. Again, you do not have to focus in on calculating the units. It is something for an advanced class, but one I wanted to preview here in the perfect practice. Okay, and then I believe we have one more question. It says using the equation for number 5, calculate the Kc. If the equilibrium constant for the substances, I think I copied this one down wrong too. It says calculate the Kc if the equilibrium constant. Wow, that one's a complete rework. So let's redo this. Calculate the Kc if the equilibrium concentration of the substances are. There we go. Okay, so once again, we're going to use the expression that we found in number 5. So Kc equals the concentration of SO3 squared divided by the concentration of SO2 squared times the concentration of O2. Again, I'm going to put in the numbers. Point, oops, 197 moles per decimeter cubed divided by 0.407 moles per decimeter cubed squared times 0.315 moles per decimeter cubed. Going to the calculator, 0.197 squared divided by, open parentheses, 0.407 squared, close parentheses, divided by 0.315, and I get 0.743. 0.743. And again, the units are going to be the same per mole decimeter cubed. All right, we've gone through several examples of all of the math from this unit. Please make sure that if you have any questions about the how or the why, that you jot them down off to the side and you're prepared to share them either before class, after class, or during class.